Welcome, and today we have with us Professor Lawrence Krauss from the Origins Project at the Arizona State University. Lawrence is a theoretical physicist. Paul and I tend to be what we call observers, and so we have a very different way of looking at the universe as we're going to explore the topic of inflation. So, inflation we've been talking about as a way to sort of make the universe sensible as it starts out. So, do you see the evidence for inflation being strong?
Well, it's grown a lot. Inflation was a beautiful idea, actually an idea in search of a theory for a long time. As you've probably talked about, it's the only fundamental physics way of understanding the smoothness of the universe and the apparent flatness of the universe, all the paradoxes of the Big Bang. It's a beautiful idea, and it kind of smells right if you're a theorist. But the problem is we didn't have any direct theory that predicted it. And other than post-dicting these notions of flatness and uniformity, the question was, did inflation make any predictions which could be tested? Because that's the key aspect of a really successful theory, is it's got to be falsifiable.
Yep.
One of the early predictions, besides flatness and isotropy, is the notion of the generation of primordial fluctuations, which would later collapse to form all the structure we see in the universe today. And inflation predicts such fluctuations and such structure in a really beautiful way. In fact, by using quantum mechanics, remarkably, what it does is it turns quantum fluctuations in fields during the period in which the universe is expanding into classical density fluctuations. If it's really true, then we're all here due to quantum fluctuations, which I find amazing. There are characteristics of these quantum fluctuations in inflation that are testable. The first is that they predict so-called adiabatic density fluctuations, and that they're Gaussian. They're Gaussian random fluctuations. Those are properties of quantum mechanics. When we look out at the microwave background, radiation, one of the key aspects of that observation is to look at those primordial fluctuations as characterized in temperature differences across the sky. And amazingly, all the characteristics of those fluctuations are in agreement with inflation. And so I'd say that once we tested that with great accuracy in the CMB, the stock in inflation went up.
So one of the things you said was that this is the only way to test with particle physics theory. So I want to probe that. Is it really the only way? It's certainly the only way we seem to have right now, but some people are out there doing other things within that regime to find another way to give you essentially the same answers.
Well, you anticipated what I was going to say, because I want to be clear and honest about this, because inflation the predictions of inflation are in agreement, great agreement with the structure of the fluctuations that cause microwave background. But what you didn't give me a chance to say is that they could have been in agreement even if it had been different. Inflation is a very robust theory, but at some level it's malleable. In particular, the nature of fluctuations that are produced depend upon the specific inflationary model, and we don't know the inflationary model. So if inflation could have agreed with more or less anything we saw, you might say that's not a very robust test of inflation. But there is a more robust test of inflation, and in fact it's what many people would call the smoking gun that we've been looking for, which is the fact that inflation generates not just density fluctuations in all fields, it generates fluctuations in gravity. And those get turned into gravitational waves. And inflation unambiguously predicts a spectrum of gravitational waves, which is independent of all the detailed models, the nature of inflationary models. The scale of inflation determines the intensity and amplitude of gravitational waves. The spectrum is basically flat on the sky. It means it's the same power on all scales. And that prediction of inflation is robust. Namely, it's not model dependent. And that, once it was recognized that was the case, and it was recognized that you could look for that signature in the microwave background, there's two ways, of course, to look for gravity waves. We look for gravity waves directly on the ground with large-scale interferometers, and Australia plays a role in that, in fact. But it turns out that those aren't really sensitive to the kind of gravitational waves which are very long wavelength, that are residual waves from inflation. And you might look for it in time variations in the millisecond pulsars or binary pulsars. But again, they're not yet sensitive. But the gravitational waves that come from inflation produce two effects. And I'm happy to say about 30 years ago, we predicted one effect, which is that gravitational waves are quadrupole waves. Namely, they squish space in one direction and they stretch it in another.
Yeah.
And what they would produce effectively, if you think of the last scattering surface where the cosmic microwave background is produced, if a large-scale gravitational wave comes by, an electron, which is about to scatter radiation towards us, would see a hotter universe in one direction and a colder universe in another direction. Well, that will be reflected, in a sense, in direct anisotropies in the microwave background. And if gravitational waves are big enough, then you can see it. And we argued, in fact, if the scale of inflation was high enough, they could have accounted for all of the initial anisotropy that was observed by the COBE satellite in 1992, which really was mostly sensitive to quadrupole radiation. But it turns out, and we've now looked at the microwave background a lot more in the last 30 years, and those anisotropies are not seen. Okay, but the same kind of squishing and stretching means that an electron will see higher intensity electromagnetic fields in one direction and lower in another. And if you think about it, when it scatters radiation, it will produce radiation that is polarized when that radiation comes towards us. The electric fields will be stronger in one direction than another direction. And it's that polarization that has a very particular characteristic. It's kind of a twisting pattern. Right. That other sources don't produce that kind of twisting pattern. And so once it was recognized that gravitational waves from inflation could produce polarization in the microwave background, that became the holy grail. I would say that for all cosmic microwave background experimentalists, that was the next great leap forward. And so there were a lot of experiments developed and ongoing experiments looking for that, because that would really be the smoking gun. This year, in 2014, earlier in the year, an experiment, the BICEP experiments, BICEP 2, reported a result which looked exactly like gravitational waves from inflation. I mean exactly. The characteristics on scales and the spectral characteristics were identical to what you'd expect from inflation. It was a surprise because the amplitude was so high that we might have thought some other experiments might have seen it, like the Planck satellite, although there were reasons that it might not. And it was a real shock to people. And I must say, people got very excited. In the interim, it's been recognized that potentially polarized dust in our galaxy might mimic the signal, not all aspects of the signal. And frankly, when I look at it as a theorist and an observer, you may feel differently. I would still say the characteristic signal, the signal, look more like inflation than dust, but it could be an unfortunate accident, and it's up in the air. By the time this airs, this will be resolved probably, because the Planck satellite is doing measurements of dust in a better way, and other experiments are looking at polarization. And we should know, I would say for certain, within the period of a year, whether this signal is real or not. And if it is real, it'll have changed everything, because that will mean that in principle, inflation really happened. And we know it empirically, as well as being the best theoretical model of the early universe that we have.